afternoon session. We'll start with a talk by Rifath Khan, who is doing his PhD here with Aaron, and talking about this. So take it away.
So the theme of this conference, since it's semi-classical gravity and black hole thermodynamics, I'll be focusing on the first part, semi-classical gravity, and there'll be like two parts of the talk. First part would say how semi-classical gravity emerges from the Wheeler-DeWitt wave function, and then second part about a bunch of things. Yeah. So first, I'll start with motivational questions. Where's the chart? So before that, let me just straighten out what I mean by semi-classical gravity. So classical gravity, you have this equation right. Where gravity is classical and matter field is also classical, and then they obey this equation. Fine. Now, then you have you can quantize the matter fields in a fixed background, and that's quantum fields in curved spacetime. While the quantum fields they don't back react on the metric. Now, if you want to know what is the back reaction, then how would you use this equation? Where on one side of the equation you have a classical part, the other side you have a quantum mechanical part. So the next thing to do is take an expectation value of this, and that's semi-classical gravity. That's what I will mean by semi-classical gravity throughout the talk. Cool? Alright. First question number 1. Semi-classical gravity, like ideally, how would we think about it coming from some place where both gravity and matter fields is quantum mechanical? Yeah.
Can I no. Expectation value with respect to which state?
Of what state you're considering. If you have a manifold, you will have a QFT state, and with respect to that state.
Okay.
And the state must satisfy the equations of QFT in space-time, which is the thermodynamics equation. I'll come to that also.
Okay.
Yeah. Cool. So how does semi-classical gravity emerge from a theory of quantum gravity? Which in particular I'll be considering the canonical theory of quantum gravity, where the states are given by the Wheeler-DeWitt state. Which is a superposition of metric and matter fields, where this metric and matter fields is on a 3-dimensional manifold, sigma 3, and this is a state in a 3 plus 1 dimensional theory of quantum gravity. And question number 1 is, how do you get from here to here? Okay? That would be mostly first part of the talk, and few more questions.
If this is the how, you should ask when, right?
How and when, everything, yes. So,
Who?
and who? Why? One more thing. This is a 3 plus 1 dimensional theory. This is a 3-dimensional manifold. The metric and matter fields on a 3-dimensional slice. How does the extra dimension or a notion of time emerge from these things? Or how do and like this is the wave function of the entire universe. Then how does the notion of observers or detectors or experimental apparatus or everything emerge from this? Where does all of that fit in? That's one question. Question number 3 is, if we live in a closed universe, then in quantum cosmology, like this is it. We have one wave function of the universe. Like for example, what?
Sorry. Maybe my knowledge is limited, but from my understanding, 3 plus 1 decomposition of the action is already, there is time. It's like in the.
Yeah.
So,
but in this object, this is for example closed universe. You're just given one functional of metric and manifold defined on 3-dimensional manifold. You don't yet have a 3 plus 1 dimensional manifold. You don't yet have a 3 plus 1 dimensional geometry. So where does that come from? From this object. That is a question.
So you get the extra dimension, the plus 1, you get it as an emergent from this 3-dimensional manifold.
that depends on the answer, and this is a question for now, and I'll come to the answer when I say that. Yes. Okay. And this is the second question. The third question, yeah. So if in quantum cosmology, for example, if we live in the state of the universe is described with the unlocking state or the Willinkins wave function or something, so that's one state. You declare that we live in one wave function of the universe, that's one state. And suppose we live in a closed universe over here, how the galaxies and all of the stars could be in many different states. How does all of those many states fit in this one state? That's one question. Another question. 1, 2, 3. Oh yeah. So closed universe, they have no boundary. So then how would you do holography? What about de-Sitter holography? And since nothing is happening over here, like where does this notion of measurement or the Copenhagen interpretation, they all fit in? These are some of the questions which I want to know the answer to, and we'll see. Part 1 will be addressing question number 1 in a slow-paced way. Part 2, I'll talk about question number 2, the rest of the question in a fast way, depends on whether I get to it or not. So, alright, now the talk begins. So let's think of a simple model in quantum mechanics with which we can like sort of understand few features about these things. For example, in the semiclassical gravity, look, you have gravity and you have matter fields. One thing is classical, the other thing is quantum mechanical. In order to understand how this classical and quantum mechanical stuff emerge from a thing where you have everything to be quantum mechanical, consider two particles, normal quantum mechanics, whose position is small q and capital Q, of mass m and mass capital M. Like for example, the hydrogen atom. And remember, hydrogen atom, you treated the proton to be classical and the electron to be quantum mechanical. Why? Because the proton had a huge mass compared to the mass of the electron. So it could be that. So now start with state psi, which depends on both of these guys, time also. And you know that this state satisfies the Schrodinger equation. We'll have an Hamiltonian, which I'm going to call a class, which should have kinetic terms for the heavy particle and some potential terms. And another Hamiltonian, which I'm just going to call as quant for now, will have kinetic terms for the small part and potential terms and interaction terms. Okay. Now, so this is a scenario where both of them are treated quantum mechanically. How does classical mechanics of just this emerge and this remains quantum mechanical?
What do you mean by merges here?
So you have the psi and do something to it in which you get some formalism which you think is the description, classical description of this thing. Yeah? Why?
Well,
It's an approximation.
Merge as he continues to.
I think he means for what kind of states would it behave that way?
Like for example, this chalk is actually described quantum mechanically.
The degrees of freedom that will
Be like classical.
Okay.
For example, this chalk is actually described by a quantum mechanical state. But you can also describe by classical states. Why? Because of something called WKB approximation. Many ways to do it. WKB approximation is one in which I could understand this but in a straightforward way. So I'll do a WKB approximation where the psi is written as e power of S and S is expanded in terms of, had I expanded in terms of h bar, both would be classical, but I'm going to just expand in terms of the mass. It is 0 m. Yeah. And power 3's expansion, and if I plug this side into this equation and then solve for it order by order, just by doing some calculations at the leading order, what I get is S0 does not depend on small q. So S0 is just a function of capital Q. And on the next order, what I get is but V class is just a classical, V class is the potential term in this H class, and I get this equation. S naught is something that satisfies this equation, and this just comes from the next order term of the Schrodinger equation. Alright? Now what is this? It's nothing but the Hamilton-Jacobi equation of classical mechanics. Where the momentum is given by dou S naught by dou Q. And what is Hamilton-Jacobi equation? Like, if you have, let's say Q, and if you have this line at one particular point, the P gives the, from S naught, like from any function, you can do some construction. You just say that, okay, I'm going to take the function, differentiate it, and that will give me the time derivative function. So from here, you know what would be the next Q. And then you take that same function in a different time, take its derivative, so you know what it is in the next place. Either you can construct a particular path, but the fact that this path satisfies the equation of motion is equivalent to choosing special function which satisfies the Hamilton-Jacobi equation. That's it. And it is in this sense that classical mechanics at this order, the classical mechanics of just this 1 degree of freedom emerges from quantum mechanics of both degrees of freedom. Alright? Now,
Rifath, can I ask?
yes.
So this shows there is a class of states.
Yeah.
Which,
For which you can.
gives you classical physics.
Yeah,
but
yes.
This doesn't really ask the question of why that class is relevant to the real world.
Because only that class emits classical description.
Okay, but I guess I'm asking why is the world classical?
Because we live in states of that class.
So why?
That if not, we wouldn't be doing physics.
So why don't we see superpositions of states in this?
You can general state could be superposition of many states, and some of them could be a WKB or not. So it could general state could be written as a superposition of many WKB states. That could also be the case. I'll come to some of those boosting interpretation later. Go on.
But at this level, the semiclassicality is already implemented in the S. You have an expansion in terms of the mass of the classical quantum mechanics.
Yeah.
So it's natural that you will have only dependence on the classical sector.
Yeah. So
it's-
this term is natural, yes. And now, where does the quantum mechanics, now what happens to this guy? For that, we need to go to the next order. And in the next order, you get an equation of this type. This is small psi, that is capital psi. I will define what small psi is. Just from the capital side, just take e to the power of I by h bar S1 and multiply it with the normalizing factor, which is just the integral of mod of this one. So this will depend on this capital Q, this normalizing factor. And this object from the next order of Schrodinger equation satisfies this thing, comes out of a calculation. Go on.
Should that expansion be 1 minus n because n is large?
Yeah. 1 minus n. Thank you. Yes. Basically m S0 plus S1 plus 1 by m S2 blah blah blah.
But I also have a question. So if small m is small, why don't you use that as an like expansion factor? Why are we expanding around big M?
We can do that and see. But basically I'm secretly expanding about the ratio capital M by small m.
Yeah.
Navigable approximation is always done where, with the expansion with respect to a dimensionless parameter. Sometimes we abuse that and do things like this, but usually it's like when such an expansion exists, then what are the consequences? That is that thing. Anyways, for now I'll just abuse it and do it like this. Okay, we get this thing. Alright, fine. What is this? Okay, this is some psi of q comma q, and you should comma t. You should interpret this as like this has the statistics of the probability of position and momentum of this guy when this, in addition to the Hamiltonian of this own system, there's one more thing which provides some sort of a classical potential. Like for example, the proton provides a it's like treated classically and provides Coulombic potential in which this is supposed to be quantized. Fine. So far, fine. Now,
Wait, if n is just a capital N is just a normalizing factor, why does it have its own kind of dynamical term?
it comes from the calculation of the equation. N depends on q comma t also.
Okay.
Yeah. Right. Now, let's consider a state. Imagine the whole universe had only 2 degrees of freedom: the small q, the capital Q, and nothing else. Then what? And consider a state where this is a stationary state, like h psi equals to 0, kind of like the Wheeler-DeWitt state. Want the 0 right now. Alright? Now what? Now you get this to be 0. This will not be there anymore. This is gone. Alright, you have this thing. Fine.
So you're implicitly assuming at this point that it's not like the hydrogen atom because you have some continuous spectrum there?
Yeah. And also like I want it, for some reason, which will be clear in the future, I want it to be normalizable with respect to small q but not capital Q, but I'll say this is a point in, later in the future. So it's deviating from the hydrogen atom, yes, but I'm just trying to say it in language where
So I took the hydrogen atom and looked for a zero energy state relative to some 0 point. Generically, I find no solutions if I was in it as a cathodic part, right?
yeah. I mean, okay. And
So we're assuming the Hamiltonian is more general,
okay.
so that there exist solutions.
So one more thing, in hydrogen atom you would also impose boundary conditions for capital Q, that psi goes to 0 when capital Q also goes to plus or minus infinity. Here, if you don't do that, then maybe you'll get more solutions, which will not be the solution of hydrogen atom, but we have to see.
So far, this is standard. Right?
Standard
This is like
model
Mott,
quantum mechanics.
This is the multiple chamber and the Cauchy-Kiefer kind of banks when you apply it to gravity, right? This is going to be where you get this time from this
Yes.
differential.
Yeah.
Who was the first name you mentioned?
I think banks.
Before Kiefer, you mentioned another name.
Mott, the bubble chamber stuff. There's a.
Oh, Mott.
Yeah.
Mott, okay.
I don't know that part. Could be, yes. Okay, and now, okay, fine. So at this step, in such a universe, what should we consider as time? Now I'm going to take a strictly operational notion of what time is, as just being the number shown by a clock, which is nothing but a physical system, which is made up of the same kinds of particles which you and I or any physical system is made up of, which for which we would use quantum mechanics to describe. So in principle, like even for a clock, you can write down a quantum mechanical state, and now you're using it as a clock. And how is that possible? You should only expect that only in a classical limit, because all the clocks that you're using is classical, right? So that whatever that device is in the classical limit, it spits out a degree of freedom, which you can use as a proxy for some notion called time, for which you have thought to be this such and such and so. So in that context, in this universe, can we use the only thing that is classical is capital Q, and can we use that as proxy for time? Let's say we do, then what? I want this guy to be positive, and the other also, and let me not go into the details, but basically if I take capital Q and define another parameter tau, which is basically that is in this particular way. Then what happens? I mean, this is what WheelerDeWitt tells us to do in their first paper. Then this becomes nothing but dou by dou tau, which I bring to the other side of the equation, and I get dou sin phi dou tau. And in this context, that in such a universe, this is the classical part, and the quantum mechanical part obeys an emergent equation, which is a Schrodinger equation of normal quantum mechanics. Alright?
I mean, crudely speaking, you want the clock to be able to have different values.
Yeah, so this capital Q also will have different values, right?
So it's like the hydrogen atom is moving around.
Now I'm deviating a little bit from hydrogen atom, but capital Q is just a real line. So
Okay.
depending on what point capital Q, what element of the real line it is, that is the time of the clock. You have a question? No. Okay.
Sorry, you said this is what somebody says to do in their first paper.
WheelerDeWitt.
It's in the WheelerDeWitt paper.
Yeah, the first part one of Kevin.
Just do it.
Huh?
It's not Wheeler-DeWitt, just do it.
Yeah, okay, fine. Bryce DeWitt.
Yeah.
I think Wheeler also did all in my report. Bryce DeWitt. Yes. Okay, fine. All right. Now let's look how things look for the case of gravity. For gravity, we have the Wheeler-DeWitt equation. Now, how can we do an approximation in which the Wheeler-DeWitt equation, which is basically a function of the metric and matter fields, spits out some sort of approximate state in which the gravity part can be treated classically and the matter part can be treated quantum mechanically by doing similar eikonal approximation where you expand S this time in powers of G Newton. Power of what? 1 minus n. Right? What? N equals 0. No, n minus 1. And look, why did you say that? Okay, fine. And working in regimes where G Newton is like relatively very small, that will be. And all that again, just plug in to the Wheeler equation and order by order, what do you get? You get in the order of G Newton power of minus 2, you get delta by delta phi x, S naught equals to 0, meaning S naught, which is supposed to be a function of the metric and matter field, is just a function of the metric, and the order of G Newton power minus 1, you get this equation. This equation, which is nothing but the Einstein-Hamilton-Jacobi equation.
Sorry, previously you corrected n minus 1 to 1 minus n.
Yeah, more than m is large.
Do you really mean n minus 1 this time?
1 second.
And those two.
1 by G Newton S0 plus S1 plus G Newton S2 plus dot. You get it? I have to think to do this.
It's at minus 1.
Well, it's like this. Okay. Anyways, so we get this equation, which is the Einstein-Hamilton-Jacobi equation. S naught is the Einstein-Hamilton principal function, and from S naught you get the pi AB. By taking its derivative, x. No. And how do you? So the Wheeler-DeWitt equation gives this, gives which is also functional of the metric just on some slices. How do you construct an three-dimensional thing? Via this. Now what you do is, for example, now here's a procedure. You take some slice, plug in whatever metric you want, plug it into the Wheeler-DeWitt state. It will give you the S naught, and look for its derivative. It will give you pi AB, and from pi AB you can get KAB, the extrinsic curvature, and from KAB KAB is supposed to be like this. If you had a classical manifold with a classical geometry, KAB would be like this. Now you do not have that. These things, the meaning of these things, it inherits them from KAB, which inherits this notion from pi AB, which inherits this notion from this derivative, which comes from the Wheeler state. That is how you have to think about it. Now the shifts and the lap are gauge equation of freedom. For simplicity, choose shifts to be 0, that depends on your foliation. Let's say you are in that particular foliation. And now over here, and laps to be 1, so this becomes tau. I don't know if it's like this half hour or whatever. And so the KAB will tell you how GAB would have changed with respect to some parameter which inherits notation from the KAB itself. And so you can know what is the metric in the next slice. And now repeat the process. Take the new metric in the next slice, plug it, and you'll know what is the next, and in that way you stitch an 3 plus 1 dimensional metric from S naught. And thus, a classical geometry emerges from a Wheeler-DeWitt state in that sense, if it allows you to do all these things. Alright, if it is such a state which does all these things. Cool? Yeah.
I have a question. Where does KAB comes from? Like, how is this related to PAB?
Pi AB.
Is it just pi?
K.
Pi AB.
It is GABCD pi AB equals to KCD. Some factors of G Newton somewhere, I don't remember.
Okay.
Alright, go on.
I'm just a little confused about the setting of the laps and the shift, because I thought that in the same way that we did there, there would be a time that would emerge for the Schrödinger evolution of the matter degrees of freedom that would depend on S naught and GAB, and that would give you some notion of time separation, but you seem to have fixed the laps.
Is this, no, the laps fixing I'm declaring, which I'm free to do. And this notion of this time is the same thing as one thing, the next equation I'm going to write down. The same.
So you can still do that. Even if you have this time, you can still choose any laps you want.
The proper time depends on how it is foliated, it's invariant, and how it looks depends on what quantum system or what kind of foliation you're doing. And I'm doing a special foliation in which the KAB directly gives this thing, but I could have done a different thing also. That's it. I did not think about the different thing, but can be done.
So did you write this in for now?
That is next order. I will come to it. This thing. And now, okay, that's classical geometry. What happens in the next order? In order of G Newton to the power of 0, I get the following formula. After again defining psi to be some n, which is function of G, e power of I S1 to G comma phi. So this will be a function of phi comma G. I get I G A B C D. Small psi, capital psi. So the next order I get this equation, psi is defined like that. And now this is nothing, not yet. Okay, this is equation, fine. Now what is this? This is now GABCD times, this is nothing but pi AB, and that is related to KAB, and that one would be related to dou T GAB plus laps to such up to 0, and that by chain rule becomes this equation, which is the Tomonaga-Schwinger equation, which is the equations of Q of T in Cauchy spacetime. There may be problems with this equation, but not going to address that.
I think the last time you tried to tell me this, I couldn't understand what this equation actually
Yeah.
means.
So for me, this equation is like, see, if you have a state over here, and if you want a state over here, you can, in Q of equals spacetime, this is where you have a background manifold. Then you do path integrals, fine. And what happens if you do this? And then that minus the initial thing divided by the difference in the limit of the difference going to 0 is defined as the function with respect to this thing, and that is this. And if you have problems with this equation, that is, we'll talk about that later.
Yeah, I guess I found it dubious.
Yeah, it's fine.
Because, I mean, it's, when you're changing, going from one slice to a different slice with different geometry, is that really?
No, I don't know. I wouldn't be able to address those concerns of thermodynamics equations right now.
Is that really, yeah, something that you
But something like thermodynamics equation, we should try to make sense. So whatever needs to be straightened out has to be straightened out.
But this is still standard, right? It's still Kiefer, everyone still does the Paradox-Rifath
Yeah.
from this, right?
Yeah.
So wait, where am I supposed to see the expectation value of the stress energy tensor in this?
It hasn't come out yet.
Okay,
Yes.
you're still heading there.
Yes. So this is so far what has come out from the Wheeler-DeWitt equation is QFT in curved space-time, and classical geometry which just obeys the classical Einstein equations. This is equivalent to the classical Einstein equation. For semi-classical gravity, let's do the following.
Sorry, can I ask, I'm a bit confused, so I'm not sure I'm asking this question very clearly. Referring to that top picture with the initial surface with G, and then you inferred all these later surfaces by inferring what is the extrinsic curvature in terms of this pi and so on. Okay, I'm not sure how to ask this, but what determines the initial surface?
Anything. You pick no, so you have to think of the Wheeler-DeWitt state as the G and the sigma 3 to be in some abstract manifold, which is not yet to be thought of some Cauchy slice embedded in some a priori given manifold, because you do not have an a priori given manifold. And in that, put some G and do this thing. If you are allowed the semiclassical approximation, which depends on the state, then it will give you what is pi b, and whatever classical geometry it corresponds to, that abstract manifold could be thought of as being embedded in this emergent manifold, such that you're choosing the slice with in which the metric is the one that you chose over here. If that makes sense?
Okay,
Yes,
well,
but-
it certainly helped me understand what you're saying, but I'm not sure I fully understand.
Right. We can go into we can expand the details after the talk. Go on.
So in the space-time that emerges like this tau coordinate is some time. That is like the proper time of the matter field.
Yeah, proper type in the background geometry that emerged. Yeah.
Yeah, the time that this matter experiences.
Yes. Yes. All right.
Don't we need lapse and shift choice?
Yeah. So I made the choice that the shifts is 0 and lapse is 1. We need that choice. Yes.
Could you make a different choice?
I mean, we could, but I didn't think.
Can you just have another description of the same space-time? Or
Yeah.
whatever? Because I mean, it's not completely obvious it would be the same because your new metric will be different. And you have to go to the wave function to find out what the new extrinsic curvature, or to the action function.
No, the extrinsic curvature is given from pi a, which is given from this thing. That is fixed.
But I'm saying, it depends, where are you gonna evaluate the derivative of S with respect to the metric?
In the hypothetical manifold. For
Yes,
S
no,
naught.
but I'm saying, if you choose a different lapse and shift, you'll have a new metric, so you'll be evaluating that derivative at a different
No,
location.
it does not do anything to this. It only would change this equation.
Wait, I was talking about constructing the space-time. that you
Is
were
the
talking about
statement
before.
that KAB is a function of GAB, and then you try to stitch it together using that data?
What does that mean?
I mean, the original wave function includes amplitudes for lots of different metrics,
Okay, fine.
right? Otherwise, you can't do this because you're using the same state for each of these slices. So it's the idea that you want to construct a 3 plus 1 dimensional manifold with the property that whenever you pick a Cauchy slice and it's of a particular metric, its extrinsic curvature is given by that expression you worked out.
Yeah.
And how do you know that's always possible?
Because that's how you construct it.
What I saw you do was construct
from this, everything comes from this.
And what I saw you do is construct pi AB
Yeah.
as this operator acting as GAB. But what tells you that it stitches into a classical
You
variable?
make it stitch into that process in the way that I described, like that.
You can assume it does, but how do you know something doesn't go wrong?
That being okay, probably it might go wrong if you think about it in detail. I don't know. but this is like the same thing. But for now, based on coarse-grained thinking, it's like this. You know what is the derivative? You know what is the next thing. And in the next thing, you know what the derivative is because S0 gives that, so you know what the next thing is. This kind of argument is what I'm doing over here.
Yeah, so I guess if you only flow along a one-dimensional family of surfaces and think of it like an ODE, then presumably it works at least usually for some finite amount of time at least.
Yeah.
But it's thinking of it like with this functional derivative sense of thinking it has to be consistent no matter which slice you pick, even when they cross each other. That's the thing that seems not at all obviously classically.
But the problem is that there is no
Okay.
unique sense of what's the next thing, right? The
Yeah,
next
okay.
thing
This is like
depends on the
locally you
lapse
know
and
what to
shift.
go to the next thing, and then in the next, probably you can choose a different choice of lapse and shifts, maybe like that. Go on.
We started with a state that was like superposition of measuring matter fields, and then all of a sudden here we have this equation of this like equation for a wave function that looks like the Schrodinger equation for the matter field on a fixed background.
Yeah.
So where in these steps did we fix the background? And we're not taking superposition.
In the choice of S0, if given a Wheeler-DeWitt state, it may give a S0, or it could be Wheeler-DeWitt could be a superposition of many WKB states, and one WKB state gives a S0. So from the state S, which is equal to e power of is, look at the S0, and from the S0 you get the spacetime. So you get it from the Wheeler-DeWitt state. Yes.
Yeah, sorry, can I, going back to my earlier question, but related I think to something Aaron said. When you choose this initial surface that you've labelled then the top diagram G, right? Are you making an assumption that your psi function is peaked at that G or something like that?
Very good. I forgot to say that. So again, everything is clear, easy to explain in the toy model. Like in normal quantum mechanics, psi x. If you look at the S0 over there, and dou by dou x of S0, only in regions where this is like where, for example, if you have the mod psi squared to be like this, and in the limit it would be peaking over here, and only in this region this would be real. And so what happens in normal quantum mechanics is that the derivative of the S0 with respect to x is in general complex, but in the point where the particle gets localized, over there it takes the real value. So in the same way over here, what I want to do is that you have a superspace which is the set of all possible geometries, and in it you restrict to a subspace which I'm going to call a semiclassical superspace, in which delta S0 by delta GAB is real, and only in that subspace you have the classical emergence. Yeah.
That condition just says the same as the peak is
Yes.
is necessary for
Necessary.
Yeah.
But it can't
And
be, it can't be two peaks because otherwise they'll get spread and they conjugate momentum.
Yeah. So minimum uncertainty principle. Yeah. So I will say something. I might forget to again address this, but I will come to that point. But ask me again.
And I also, I'm still not quite sure I understand this tau here. If these are quantum fields, you said, well, I should think of this tau as the proper time of the matter.
In the background geometry, in a
But
slice. Yes.
these are quantum fields, what is the proper time?
This is but you have a classical geometry background where you have a proper time.
Not yet, I just have a 3 geometry and you're telling me how to build.
Yes, and once you build a 4 geometry, you have a 3 plus 1 dimension geometry in which you have a background. So that any path, you have a classical 3 plus 1 dimensional metric. From with respect to that metric, you have to look at the proper time.
The assertions you cover this after you construct that.
Okay, I see.
Okay. Now, so now let's go to semi-classical Einstein equation. For that, I looked at. So I was thinking what to do, and actually came across one of Hallibur's paper where he spoke about Wigner function, and then I was able to proceed. Wigner function for normal quantum mechanics is for q comma capital Q comma small p comma capital B. Let me just write down a function in the phase space, which is like this. Ly pi h bar square integral dx dy. So this is a function in the classical phase space, and now this is a nice function which is which wants to be interpreted as a probability distribution function even in when the state is quantum mechanical, but not quite so much. So it's a quasi probability distribution function, which means it violates it can become negative and it violates the third axiom, the sigma negativity. That's fine, but in the limit of h bar n to 0. This becomes a probability distribution function which satisfies the Wheeler-DeWitt equation, which tells how the probability distribution function in the phase space have to evolve classically. So let's use this function. Fine. Now I wanted a function, some kind of thing in quantum gravity. Sorry, not quantum gravity. For classical gravity, I wanted a Wigner function. Ideally, I should look into all of that and construct a Wigner function. I did not find it, so now I made a jump in which the Wigner function for quantum gravity, let it be this thing: g comma phi comma pi comma pi phi in the same mathematical expression. It could be wrong, but whatever. I'm going to proceed in this momentarily.
Sorry, what are you trying to do now? What is this?
I'm considering a Wigner function of a Wheeler-DeWitt state. Why? It will be clear now.
Okay.
And he mentioned the work of Halliwell, right?
Yeah.
Yeah.
Halliwell was talking about a classical Wigner function. We have to use that in some paper, something like that. And g plus h comma phi plus phi tilde g minus h comma phi tilde integral phi a b h a b plus phi 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 tilde. Let this be the Wigner function of the Wheeler-DeWitt state. We can all do analysis of it is right on or not, like, and now, but what I want to be remembered in this talk is the story of what we are trying to do and where this is going. That's most important. Now over here, Wigner function is basically like, see, what do you want in quantum mechanics? You want the statistics of measurements, right? That is nicely captured by the density matrix. And density matrix, some sort of a transform of that is massaged into a Wigner function. That is it. Now in this, so if you have two systems, if you are interested only about the first system, you take the reduced density matrix of the first system. Similarly, you take the reduced Wigner function of the gravity, alright, just the gravity, by integrating out the phi and phi phi. And now in this step, I'll do some fast manipulations, which if it is not understood is fine, but just get the gist of it.
Before you do that,
Yeah, go on.
Should I be worried about g plus h not necessarily being a Riemannian metric here?
I don't know if you have to be worried about that, but G is Riemannian. Maybe take H2 will also be Riemannian such that G plus H always belongs to the superspace. Maybe you have to do that.
You're integrating over
respect-
h.
Yeah.
and
The
that
space
means
is
all
locally,
sides.
the space is locally convex, so if you just make your h close enough to your g, then you'll be
And if
fine.
you're in a linearized approximation, if h, you can assume h is small compared to g, it's not an issue. But if you allow h to be of the same size as g, I don't necessarily end up with a Riemannian metric at the end. So
It's like that. Even if H is just Riemannian.
Yeah, it's a
Fine.
cone.
So then let me say like this.
Riemannian metrics and I subtract one from the
Okay.
other. I could get a Lorentzian or
Yeah.
something.
Okay. Let me say like this. H belongs to whatever set such that G plus H is a Riemannian metric. Like that.
Maybe you can argue that the integral is dominated by small h's.
Let me come to one step. Maybe that is what is actually
If it is
happening.
dominated by small h's, then what you do about the rest may not matter. Although strictly speaking, you'd implicitly need to be doing something about the rest
Sure.
in order to say it's dominated by small h.
Sure.
let me do one step over here. Maybe it is that thing, and then maybe we'll be like, that is what you're doing. That's good.
Related to the point about you having your side having to be peaked around a certain G.
I know. Okay. Now I'm going to do some fast manipulations over here. If you don't get it, it's fine. But the next step will be important. Now, let's integrate pi phi out. Boom. It becomes a Dirac delta in phi tilde. And when I integrate, this be phi, this be phi tilde. And when I integrate phi tilde with the Dirac function, it becomes this. Alright, fine. And then I'm going to do a power series expansion in psi in G Newton. No. Before that, I want to do a rescaling of H. G Newton H. G Newton H. G Newton H. G Newton H. I rescaled H. Okay. And then I'm going to do an expansion over here. This maybe turned out to be like that wrong interchange of integral and summation leading to asymptotic series. But fine, whatever. So
We don't know about that sort of thing.
Okay, fine.
It's hard with that, we get that sort of.
Okay, fine. Alright, cool. If you're okay with that, I was running up with that at one point, but anyways. Do a power series expansion in G Newton, just like that guy, and do a Taylor expansion about H equals to 0 over here, and then what you get by throwing away some higher terms is this line, which is delta S naught R is like S naught's real part, okay? You get this equation, okay?
I mean, the left-hand side is icon on fire, right? The Wigner function.
Yeah, good. Okay, you get this equation. Fine. What is? I actually forgot to say one more thing. Oh no, maybe I'll say it later. You get this thing. All right. This is important to say. So what it means for a Wigner function to say that spit out classical mechanics is, this is a point that I understood from Halliwell, is that there should be strong correlations between the position and so x and p. All right. So which means for a given p of g, this whole whatever is on this thing must look like a very peaked thing. In the idealized case, I want it to be a Dirac delta function peaked. All right. And for that, look, it is e to the power something times this thing. All right. Now, if the step that I'm about to do is an allowed step, then I'll go to the next thing. And what is the assumption? I'm going to take it to be the condition necessary for the allowed thing to be true.
Wait, I'm sorry, Ron, I got lost here a little bit. What is this expression on the right-hand side?
Okay, fine. So this is just S1, the real part of that. That's fine. This is just the mod psi square, the emergent QFT mod psi square. That's fine. This is like the normalization factor of 1 by constant, something like that. And yeah, go on.
And what is that whole block of text doing here? Is
Exactly.
it multiply?
Yeah, it multiplies. Multiplies. I tap on it to do something. Yeah.
So
Imagine the space is not existing, okay? This is next to it. Now, go on.
sorry, what is phi?
Phi is the phi of this guy. Magnitude.
Oh, okay.
Go on.
So what's the point of this function? Or what is
That point is coming in the next line.
Maybe we should explain for the.
I find it hard to care about it due to the computation.
Yeah, so after I say the point, then you recap about this later. Okay. So now if this is a Dirac function, did anyone else have a question? Sorry, okay. G equals to okay. Now this, oh no, wait. If, what is this? Yeah, go on. Say.
Expectation value of e to the minus.
Yeah, good. Alright. If this, emergent Q of t in curved spacetime state psi. Okay. If this is equal to e product minus I.
Wait, so is this no longer multiplying the left-hand side?
One second.
It is.
Now imagine nothing exists, only this thing, okay? If this side part is equal to this guy, if this is equal to this guy, then I now I separate this out. This is gone. I substitute it like this. Alright. So now this step, I'll come to it. This thing. Now what is this? This is nothing but okay, which tells you that, okay, fine. Now S naught satisfies the zeroth order Hamilton-Jacobi equation. So you write this in terms of this and this, and the resulting equation that you get is equals to this, and GAB times this is nothing but the derivative of this with respect to the proper time, which and from the Schrodinger, since e to the power of S would satisfy Schrodinger's equation, this effectively becomes expectation value of the matter Hamiltonian in the state slide equals to this, and now this is the back-reacted Einstein-Hamilton-Jacobi equation, which is equivalent to the semi-classical Einstein equation, that, and thus semi-classical gravity emerges from the Wheeler-DeWitt equation, and it just doesn't emerge, it emerges along with some condition which is needed for it to emerge, which is the validity condition. Any approximation has some regimes of validity. You cannot expect that the approximation is true everywhere. So you need to carefully study in what region is your approximation value. And this is a validity condition, and you need to study the validity condition carefully to understand when you can trust semi-classical gravity. That's point number 1. Alright, it's the end of part 1. Now let's go to part 2.
Wait a minute.
Yes, go on. So correctly 5 minutes, ask questions.
Okay. So you seem, if you want to say that this is the same thing as the semi-classical Einstein field equation, you're basically assuming that your Hamiltonian is the T naught component of your stress energy tensor.
Yeah.
And that's not always going to be a valid assumption.
Right.
Because you're.
But it's for every single lapse, so it's for every possible surface. So T naught generates the whole stress energy.
Okay.
But I'm sorry, I'm confused about how this, I thought you already had an equation,
Yeah.
the Hamilton-Jacobi equation
Yeah.
for the classical background.
Yeah, but it's only, and that is just classical gravity, Q of curved space-time, but this is not allowed to back react. Now I'm allowing it to
So
back
this
react.
is S1 now, this is for S1. Oh, this is for S1 of the,
Yeah.
of
And
the gravitational part.
Yes.
Ah,
The back reaction is done by this thing.
okay.
So-
Why does it come from some other Wigner function and not from the
Must come from that also.
WHIT equation itself?
Yeah, must come from that also, but I didn't see how it's coming. This was easier for me to think.
Also not if you go to subleading order.
Now that's a different interpretation for that. And the way I would like to interpret for the higher order is breakdown of notion of classically, breakdown of locality, breakdown of time, space, and all those kind of things. But that's a discussion we can have. How to interpret it's because I don't know. We'll see.
Okay, I thought that the Kiefer one did it like this, what you're saying, like higher order included the back reaction of quantum matter, but I don't remember it anymore. Maybe.
I don't know.
I'm still stuck on this Hamiltonian thing.
Yeah.
So if you you seem to be implicitly claiming that taking the expectation value commutes with choice of lapse.
The choice of labs you make. Like what you're saying. Yeah, I don't know.
Because otherwise, this is not going to give you GAB.
Okay. think about it properly later.
Okay.
Yes.
You do it for different choices of labs, and then you get a covariant in the end.
Given the choice of labs, you already fix your definition of tau, which is what enters there.
But if you really want to make this to be an operator representation of the tensor, then you want it to be the case that, well, changing your labs appropriately commutes with taking the expectation value, and that's just not clear to me that that's. I mean, it might happen. It's not clear to me a priori that it will work.
It might happen, and a detailed analysis is required. Yes, I agree. Yeah,
So
go on.
what are the conditions for this expectation of
Yes,
e
yes,
to the I
that is my
equal
next,
to the equivalent one?
Wait, let's look at the conditions now. Any question before I go to part 2?
Maybe we should write the rate definition separately. It's like you get confused by them blob there.
Yeah, I'm gonna delete this thing, and I want exactly 6 boards. I'm gonna delete this thing. Okay.
Ooh, right?
Why don't you delete the particle?
You have
Yeah.
This is always a reference.
Or
Okay.
you
So
can
you must be able to understand.
use that word.
You have
So
to
we
No,
know once.
I want those boards for something else. I'm gonna delete this thing. What I did,
Can we photograph it first?
no one likes it, fine. I will go to the next board.
I have a question. So, have you shown that like when the gravity and also the quantum field, the matter field, both go to classical? Can you show the exact classical background or classical like Einstein equation? Because this seems
what
only
I'm deriving, right? This is
no, that's only the gravitational part.
Yeah, that. But over here you have gravitation and the back reaction. Whole point of this, BB, is that back reaction is there.
This is
Go on.
the next order term, so you just get chuck that. The next order term, and then you get.
So your definition of pi is different between this line and that line, right?
Okay, fine. There will be some factors.
No, I mean pi now has an S naught and an S naught contribution, whereas in the order g n Newton to the -1,
Yes.
was just S naught.
Yeah. So this pi gets its meaning from this thing. This is always, and this always satisfies that equation. And over here, the pi that is this pi, which you are supposed to be observing, is not peaked around this, but it's peaked around a different value.
Yes.
Okay, that's the thing. Go on.
Because the thing is that S is independent of the
Yeah.
field. If the field is a classical field, then it does not include the stress energy tensor from the field.
Yeah.
Right? So what's happening there?
Okay,
If
so
you
we don't.
get-
Okay, you answer the question. Go on. Sorry, one second. Wait, go on.
No, I just asked like that S naught does not include the stress energy tensor of say if your quantum matter field can.
Yeah, does
go
not
to-
know about the stress energy quantum matter field. Yes, but it satisfies from the equation, and from this equation you get this guy, and this is the backdated Hamilton-Jacobi equation. Fine, go on.
I think what he's asking is that the vacuum Einstein equation?
Which this this is the vacuum. This is equal to vacuum Einstein equation. Yes.
But what if you have a large matter field in there?
Then you have to take the back reaction and you have to use this back reacted equation.
Even if it's behaving classically?
But the transition seems.
Even if the classical gravity is behaving classically, you have to take the back reactions from the quantum fields.
I see.
Yes.
So, what
He
is,
was raising his hands before. Go on. No. Go on.
so what is, again, what is this Wheeler function and why is it important that it's a delta function of the same classical equations motion?
So let me just say this thing. For WKB states, it becomes that, and that is what you actually mean by some classical thing. Some more philosophy is required over here.
No, but I mean it like we can construct this object such that it is equal to this, but like why is this object important? So where does it come from?
Just explain for the point particle where the classical derivation comes from.
The Wigner function.
Yeah.
Yeah, what is a big
Was
function?
the intuition.
It's an alternate formulation of quantum mechanics used in quantum optics and different stuff. I'll explain more about Wigner function later. For now, just this. Go on. Last question.
Yeah. So I think just on the logic of this board in the middle. So the first line is the definition of the Wigner function.
Yeah.
The last line is a substantive condition.
Yeah.
How did you get from a definition to a substantive claim?
This is the definition. I did some calculations, and I want it to be this thing in particular, and that is the criteria for emergence of classicality for the metric. And for that, I assumed this step, and I got this thing.
Yeah, that's like a delta function or
Yeah.
something, right?
Yeah.
That's what he's asking. Like,
There's also an assumption of a delta function on the right hand side, right?
Yeah.
So I presume we're going to integrate this function all over some space of metrics and we're going to get this because it's a delta function. So what is this integral?
How is the invariant integral defined? Good
No,
question.
I meant why is it important? Where does it come from? And why should that integral of this particular function be related to the semi-classical equations? I guess that's my
To this delta function, you mean?
Yeah.
Because only if it is of this particular form, it satisfies the criterion that you have strong correlations between the G and pi, and that is what you mean by classical emergence. More on this later.
You just think of the wave function as being peaked around a classical trajectory, and that's the condition
Think of it
that would
as-
emerge from this, in this formalism, using momentum as well as the metric.
I think it was pretty.
Fine. Part 2. Some things have to be sacrificed for the greater good. I will explain everything later on. Otherwise, I won't be able to say some points, and you won't know that points even exist. So I will, part 2, Blackwell Fermi paradox. So I don't know how I'm going to do this, but I'm just going to think it. So, summary of Blackwell. Classical gravity, no paradox. Why? Because black hole forms collapse. And all the stuff is inside the black hole. Fine, no paradox. QFT in curved space-time, no paradox. Why? Okay, black hole forms. No. Black hole is not like forming. You are just evaluating quantum fields in a fixed given background. As long as it is globally hyperbolic, you have a global unitary evolution QFT, no paradox. There's still Hawking radiation, which does not take any information from what fell in. All the information is inside, no paradox. Now, the paradox starts coming in semi-classical gravity when you allow the quantum fields to back react the gravity, and then you're saying like, okay, looks like this, the Penrose diagram. So what do we do when it evaporates? We'll do this. Okay, this is the Penrose diagram. All right. So we have this Penrose diagram for semi-classical gravity. Now, here, there is a paradox. Like it has that information over here. There's no information on radiation. What the heck happens to the information of this by the time you reach this after the black hole evaporates? Fine.
So you will be working with AD as boundary conditions all the time, or
Actually, it does not matter.
no, because of the way that you draw the
Yes.
diagram? Like
Yeah, because used to the community of ADS-CFT, and now you can do anything over here. For at least it has to be a flat space or ADS. But it's better to go with ADS. Like it would be flat space also. But the Cauchy holography thing that we did not have an explicit example for flat space, so let me just do it in ADS.
It's like for potential part 3, it's nice to just move the areas.
Yeah, we can do that. And so now we have a state over here. Alright. Now you have a Wheeler-DeWitt state. First of all, the Wheeler-DeWitt state, the way you have to think now, see, this is the point where I'm going to start, I'm going to change gears and I'm going to explain fast, but I hope the points that I'm stressing are at least the points that you get it. So now, given a Wheeler-DeWitt state, since the background actually emerges from the Wheeler-DeWitt state, it's not like the Wheeler-DeWitt state lives on some Cauchy slice. You should really actually only think about the Wheeler-DeWitt state as living on the boundary. And it simultaneously describes all possible Cauchy slices. That's one point. Alright, fine. So what, in Cauchy slice holography, I'll throw a map. Yeah, we have like constructed a map from the boundary theory and the Hilbert space of the boundary CFT, and we have a construction of the Hilbert space of canonical quantum gravity. We show that they are isomorphic to each other, and there is an explicit map that eats up QFT state and spits out the Wheeler-DeWitt state. Okay, and that QFT state can actually evolve in time, and this guy, the Wheeler-DeWitt state satisfies the boundary Schrodinger equation. Fine. So you have kinematics, that is which is given by the map, and you have dynamics given by the boundary evolution. That is a model of quantum gravity.
That was a lot to say without writing anything out of the book.
Yeah, because I'm not stressing on that. Anyways, one point is, how do now in order to properly study black information paradox, you have to do the following. Point number 1: how does the bulk emerge from the boundary theory? You take a boundary thing and you map it to the Wheeler-DeWitt state, and from a Wheeler-DeWitt state, use this construction, and this construction will give you a particular classical geometry. And if it gives you a classical geometry, then you say that the holographic state has a classical geometry dual to it. As this whole program of bulk reconstruction is trying to construct all of I was told it is the reverse, but anyways. So we can do reconstruction of the bulk from the boundary via the map and this semi-classical approximation. And it will also tell you what is the effective QF in first spacetime state over here. And that you can play around and talk about subregion duality, and I will tell you what kind of where is the entanglements of wedge supposed to be, those kind of stuff. Fine. But what is important over here? You have to start from state which when mapped to a Wheeler-DeWitt state gives you a particular state which is a WKB state and has the right initial conditions. It has the right QF in spacetime state and the classical Hamilton Einstein-Hamilton principal function, which when evolved with semi-classical gravity will form a black hole. Such a state, I'm going to define it to be a quantum black hole. Why? Because that is the thing that reduces to classical black hole in the classical limit. Is that point clear? Okay, fine. Whatever, fine. The point is, so this is, let's say this is the page time. All right.
There's a question.
Yeah, go on.
Sorry, well, first, why are you calling it a quantum black hole since it's not yet a black hole?
It's not yet a black hole. Will eventually form a black hole if semi-classical equations hold.
Okay, and secondly, so like generically, you can have a CFT state on the boundary that would define you a state, a state on the slice that would not give rise to the classical spacetime.
Yes.
Okay.
Yeah, it could be. Okay. Let's come to this condition. Now, what this condition? What was the condition? This must be equal to this. And effectively, by taking expanding e to the power of this, you get pi I delta s not no s1 r by delta g a I b I x I. This guy's expectation value minus product I equals to 1 to n expectation value of delta s 1 r by delta g a I b I x I. This must be equal to 0. This is what is implied by this condition. Yes? Yeah. Now, in the real world, it's not necessary that the Wigner function is a Dirac delta function. That is like the most idealistic case, which if you relax, we just need heavily peaked. Maybe. Now it comes to a problem about a question about your detectors. What do you consider to be the resolution for something to be classical? Those kind of things. But at least we would have this in a heavily peaked thing. So if this was a Gaussian peaked around this, that also experimentally look like semi-classical gravity only, and that will relax the validity condition. So as the validity condition as for now would be satisfied by only a measure zero set of sites. But after relaxing, it will be satisfied by a broader class. But the one thing that you cannot do is have this guy blow up. Then you don't have classical gravity at all. And for it to not blow up, this guy must at least it's not necessary for it to be exactly 0. Just let it just be of order of g Newton to the power of 0. Because if it is of order of 1 by g Newton, then it will blow up in the limit g Newton into 0, and that is what you're doing your power series expansion with respect to. And so then you will not have classical spacetime. Fine?
Is order Gn Newton's raised to the power of 0 different than order 1?
Yeah, it's the same. Okay.
Order 1 in GN.
Yeah. Yeah, good. Now, this equation, after this usual QFT calculations like one particle reducible, irreducible, correlation functions, green, connected, not disconnected, that kind of calculation, you massage it and it becomes some condition over here, which it just becomes this condition. Becomes this condition, where these are like the endpoint correlated functions of the energy, and this is a bunch of idiotic terms which just has time derivatives of either the amplitude mod psi square of the QFT spacetime state or the expectation or some different observers. and is basically with respect to the time. Alright, so all of those kind of terms are over here. Now in order to go to backward information paradox, I need to introduce some notion called sub-region classicalization.
What do the curly braces mean? Is that like an anti-commutator or something?
No, it's just a set of all these terms.
Oh, okay.
A set.
And are these H matter?
Yeah, for now it is H matter. Yes, H matter. Yes. Now, let me throw sub-region classicalization, which is important. So, if suppose, for example, a closed universe, you take this particular slice. If you're lucky, if you consider a Wheeler state in which semiclassical approximation holds throughout that slice, good. You have an emergent classical spacetime everywhere. But what will you do if it starts to screw up in this particular point? Which can happen. Why? Because, for example, you have a normal, let's say x1, x2. It could be WKB with respect to x1, but it's not WKB with respect to x2. That could be the case. An example over there. So it could be WKB with respect to the metric over here, but not with respect to the metric over here. If this is the case, then what happens, I'll just throw the result, is that the psi that you get is e power of I s naught times psi emergent, and the psi emergent satisfies the Tomonaga-Schwinger equation outside. The S naught satisfies Einstein-Hamilton equation. It's a local equation. It satisfies Einstein-Hamilton equation everywhere over here. Psi emergent satisfies the Tomonaga-Schwinger equation outside and satisfies the full Wheeler-DeWitt equation over here. And from a shaky path integral argument, it satisfies an emergent boundary shortage equation at this split. And yes, it is not a very sharp split. It all depends on the Wheeler-DeWitt state. This is just concept throwing this thing. And so what happens is you stitch space-time not everywhere, but only in the region where it allows you to. So from it emerges a sub-region which is classical, emerges a boundary beyond inside which things are quantum mechanical. This is what I mean by sub-region classicalization. And at one point, this was confusing me because with the initial data over here, I thought you can only know what is in this domain of dependence. But the Wheeler-DeWitt equation state gives you an extra information about what is the pi AB even in this region. And so it really depends on the Wheeler-DeWitt state of how this boundary emerges. Fine. Now, for the gravity to be classical close to this boundary, which I'm going to call it as, let me not call it anything yet. For this emergent boundary, for gravity to be classical close to this emergent boundary, the similar Wigner function analysis and the validity conditions are the following. It pretty much looks like this only. Yeah, pretty much looks like this. And some of the xi could be, if the xi is close to the boundary, then the h that you have to use is the ADM Hamiltonian. If xi is far away from the boundary, then the h that you have to use is the matter Hamiltonian. And that when you integrate out in under spherical conditions, you get a relation which is h black hole to the power of n, h Hawking radiation to the power of m, minus h black hole to the power of n, h Hawking radiation to the power of m, minus integral the set of all these terms to be area times order of g Newton to the power of 0. So this is a condition, if I derived it correctly, has to be right, and when violated, you have to consider that the space-time is no more classical.
What is the black hole and Hawking radiation appear?
Yeah. So the H area, when you evaluate it close to, okay, fine. So now this guy, now consider that is a screen over here, and if you want gravity to be classical close to this boundary, then you use the condition, and it is actually H area, and the H area over here is what I'm calling as the H black hole, whatever is inside that boundary, and whatever is outside, H matter I've integrated over outside, and I'm assuming that's just Hawking radiation, so it's just the energy of the Hawking radiation.
That's the Hawking. Okay, so this is making me nervous. I'm not very well to say.
Okay, that's fine.
So the Hawking radiation is in a mixed state.
Yeah.
So if you're going to restrict to the region with the Hawking radiation, don't you need a sort of generalization of this WKD formulation that includes mixed states?
I want mixed states, like
The Hawking radiation is in a mixed state.
yeah, that's
You
fine.
can't assert that the region outside this zone is a state that satisfies your criterion to be in the semiclassical regime if your criterion for being in the semiclassical regime presupposes that you can only have a pure state.
Can you not take the reduced density
Yeah,
matrix of the Hawking radiation and
story.
calculate the expectation value of the energy?
Huh?
Can you not take the reduced density matrix of the Hawking radiation and calculate the expectation value of the energy?
Sure, you can calculate the expectation value of an energy, but well, actually you can't for reasons I'll say, but let's assume you can. Then if you want to do all this stuff on the other boards, would you need a generalization to mixed states?
Okay, maybe for
No,
need
but
to
the
think
full state
about
is
that
pure, but the emergent empty state.
I
also
know,
reduce-
when he talked about, okay, this state satisfies I'm gonna expand the state, and I'm gonna assume it's of this form, he's implicitly assuming it's a pure state.
Yeah, but over here the emergent state is based, you have to think of it as a Q of t closed spacetime state outside the slice coupled to a mini Wheeler-DeWitt state on the boundary.
Yeah, it's still a mixed state.
No, but I thought
The whole state is pure state.
The whole state is, but the reduced state is a
It's a
mixed state.
yeah.
And that's the state that needs to satisfy an analog of this WKB condition, right?
No, I thought the whole state, you're putting in the whole state to calculate the expansion.
Yeah, the whole state.
Oh, your statement is that even though the state inside the region is very quantum, you can still say that the whole state satisfies this WKB condition with respect to certain variables, and those variables are restricted to the outside region.
Yes.
Yes.
Okay, maybe that works.
Okay.
And the second thing I get nervous about is how exactly are you breaking up the energy between these two
Very good.
systems? I mean,
So-
what's the transition point?
So
Is
the
there an
transition
interaction
point-
there?
The transition point is a very important point. No, I mean the concept. So now let me say that, and then I'll proceed with the talk. Everything is quantum mechanical. Some parts of the world become classical, and you get to whenever you do experiment, you decide what is your apparatus, and then what is exactly your system, and then you do quantum mechanics of your system. For example, this is your system, and this is your experimental device. Now you can choose, you have full freedom in taking another classical system over here and not describing classically, but you can describe it quantum mechanically, and that cut that you put between the classical and the quantum mechanical thing is called the Heisenberg cut, and which you can put wherever you want. The only thing you cannot do it is put beyond some point which is actually quantum mechanical, not classical. But you can move it arbitrarily to any and include anything in the right hand side of the cut, which is also classical.
That's fine, I'm fine with you making this region a bit bigger and treating the boundary on the semi-classical side, but I still want to know what you do there.
So over here also you have to you can put this anywhere with just the condition that outside this thing it's all perfectly classical. And even if it is classical inside also, you can put it over here or you can put it inside. So this is kind of like, this screen is kind of like the Heisenberg cut in a theory of quantum gravity. And it depends whether it is over here or there, depends on your choice, and up to what point you can put depends on the Wheeler-DeWitt state.
And maybe this is coming back to my first question. Does this thing emits Hawking radiation in a mixed state? Does it actually satisfy your condition? Did you check this?
I don't know, I didn't think about like that details. I need to think. We can discuss this in details.
So by here mixed states would be by truncating to a certain order in this expansion with this boundary, you would get the mixed state interpretation.
If you forget about the Wheeler-DeWitt state that lives in this emergent screen, then it is a mixed state. If you take the state which is the QFE closed spacetime state over here, coupled to tensor product with the Wheeler-DeWitt, whether you can do the tensor product or not, I don't know. But tensor product with the Wheeler-DeWitt state over here, the whole thing is a pure state. Okay. Yeah. And in order for gravity to be classical over here, or classical close to this has to be satisfied. Okay. If I have done everything correctly.
How do these boundaries relate to the horizon?
No, it does not relate to the horizon. You can put wherever you want. Spacetime is classical here, you can put the boundary here. If spacetime is classical here also, Wheeler-DeWitt state allows you to do that, you can put boundary here. You can keep putting boundary wherever you want, not beyond the point where the Arabic approximation breaks down. Similarly, just like how the Heisenberg cut,
Not beyond where?
not beyond the point where the classical mechanism does not emerge. Just like it is the system is treated quantum
So really the
mechanics.
screen should be up by the
Yes.
singularity rather than inside the
Ah,
black
that's
hole.
what, exactly. Why? Because you assume that it is all classical over here. Let me come to that point.
Okay.
Okay. Now,
But so sorry, so that means I can put my screen somewhere, maybe not close to singularity, but somewhere inside the event horizon.
inside what?
Inside the black hole.
You can, if it is classical, you can. Where until whatever point is classical, you can. Think of it exactly in the same analogy as the Heisenberg cut in normal quantum mechanics. That's why I would like to call this screen as a part of the Heisenberg cut in theory of quantum gravity. Anyways, now, if this thing is right, and now the upcoming step, I'm not sure, it's still shaky, still thinking about it. You guys can tell me how to proceed. Look, this is based, what is this? The correlations between the energy of the black hole and the Hawking radiation minus some terms which depends on like this, must be of order G Newton times area. Alright. Consider a slice over here, and if your screen is over here, there isn't much Hawking radiation emitted in early times. So the entanglement entropy between the black hole, entanglement entropy with Hawking radiation, which is the entanglement between the black hole and the Hawking radiation.
So there is no black hole yet at the
Yeah, not yet here. Okay, let me take a slice like this. So here, the entanglement entropy is basically the entanglement between the black hole and the Hawking radiation. This whole thing is always a pure state. Alright. And this whole state is always a pure state, which is just a boundary state. And this is just mapped to a Wheeler-DeWitt state. You have to consider the Wheeler-DeWitt state. Alright. And it's basically, the entanglement is small. So over here, since the entanglement between these two things is small, you can expect the correlations between those things to be small. So and for a big black hole over here, everything is like very adiabatically evolving. These are just hand-wavy arguments, I know, but fine. Very evolving, very like the speed at which they are evolving, they're at least finite kind of thing. So it is like order of this will be of order of G Newton. It's just not order. At least it's not of order of 1 by G Newton in the G Newton tending to zero limit. Fine. So okay, we can trust semiclassical gravity over here. Okay, good. Now let this black hole be at a size as big as the Milky Way galaxy. Alright. And then let it wait for a long time for it to evaporate, and by the time it reaches the page time, let it be a small thing which is the size of the solar system. Whether it's that size or not doesn't matter. But big thing evaporates, becomes small with respect to big, but still is very big. So over here, such a for a black hole of size solar system for sure, so big. So semiclassical gravity have to hold, right? Like how can quantum gravity actually make any play over there? So definitely semiclassical gravity have to hold, and so we can actually evolve beyond this thing. This is, I think, is the reasoning behind why people thought it is still semiclassical over here. But strictly speaking, in full proper moral reason, we have to check. We have to check correctly derive. If I made a mistake over here, we have to still correctly rederive the validity conditions, and then check if that validity condition that comes from this WB approximation holds over here or not. That is what we have to do. And now, look over here, when there is a slice of this point, if semiclassical gravity actually held up from here to here, then we have a QF in curved spacetime state over here, right? QF in curved spacetime state over here coupled to some mini Wheeler-DeWitt state over here that describes this whole thing. Alright. And if for gravity to be classical over here, we need this condition to be satisfied. But look, what is the entanglement entropy between the Hawking radiation and the black hole at this point? It is actually of order area by 4 G Newton. It is of the order of 1 by G Newton.
Yeah.
Like it could be half of the area of the initial thing, or just area of this particular horizon of the solar system size thing. Since there is 1 by G Newton over here, is huge. Now the shaky step that I'm about to say, which you need to think is true or not, is Does this mean that the validity condition is broken? And if it is broken, then how can you trust the semi-classical gravity over here? You do not have a classical spacetime here. What happens over here becomes a question mark, and you need to do the analysis to talk about stuff. Questions? There's more to say, I will say. Any questions so far? What?
When you say you need to check, is that because you're about to tell us what happens, or are you saying somebody will check?
What I'm saying is, I think that by the shaky arguments is making me doubt whether it is valid or not, and make the shaky argument unshaky. That's what I'm saying. Yeah, because why? Because entanglement in the systems is what is like roughly the correlations, right? And the correlations is what is like this. And this is all possible correlations. You're saying the following statement. All possible correlation functions must be of order of G Newton power 0. This is order of G Newton power 0. Why? Because even over here, the black hole evaporates very slowly, and so you can assume adiabatic conditions for this, and so these guys still are on order of G Newton. And so it would imply that the entanglement also is of order of G Newton, but it is not. So this is the shaking argument, and need to check this.
So you have 5 minutes left, so if there's anything you really desperately want to say, you should get to it.
Okay. Fine. Now,
just one thing.
Can I let the second hand clock go to 10?
I mean, I personally am happy to continue on. I just don't want to keep people here longer than was promised.
I'm just saying, do you want to leave?
No, I have a few more things to say, which I can say very fastly.
Afterwards, or
I'll say fast.
just 5 minutes till we all leave?
Are you going to say more about black holes, or should we pass on black holes?
I'll say something about quantum cosmology.
As I say, I'm happy to go longer. I just don't want to force people to stay. How about in 5 minutes? Anyone who wants to leave can leave.
Maybe I want to take the and discuss.
Okay, 5 minutes. I will summarize what are the rest of the things that I want to say in a very fast way, and no questions at that time, but I'll take questions after I say that. So, okay, so what I think right now is that you cannot do a semi-classical approximation over here. It breaks down, but still you can know what is the information over here from here via Cauchy's holography. How you do not trust the semi-classical gravity over here. You just trust the full boundary evolution, and you just take the state, which is a semi-classical gravity state that forms a black hole, and then you do evolution with respect to this state, and then hit the CHS, Cauchy's holography map at each point, and check if it's semi-classical or not, and you will get a framework to understand what is actually going on over here. And later on, if it is a WDV state, the emergent Theophane closed state would depend on, would have the information about this. Why? Because it's coming from this, which has information about this. This is unity evolution. This is in the perspective of how information comes out from the bulk observer's point of view. That's one point. Another point is, okay, this is that. Fine. So you can put a screen like this, and over here, since this satisfies the what is it called? Wheeler-DeWitt equation here, boundary Schrodinger equation over here and here. I think this can be mapped into a framework where this becomes some sort of an finite set of holography, and it is in this sense where I think a DS holography emerges in a Wheeler-DeWitt state, and a boundary also emerges in a Wheeler-DeWitt state. The holographic screen is really just a Heisenberg, is a part of the Heisenberg cutoff in a theory of quantum gravity. That's one thing. Another thing is for in quantum cosmology, you have the mini superspace approximation for a conformally coupled scalar field in chi. Over there, if you take the full solution, the most general solution, take summation n psi n of a comma chi. The most general solution, like psi would actually split into psi up plus psi minus down. One of that, you look at the most general solution and explicit calculation show what it tells you is that in this large A thing is where WKB approximation holds. Over here, for generic states, it does not hold. So my question is, if WKB states does not hold over here, the way I would think about it is that you do not have a classical spacetime here. You only have a classical spacetime here. Then what does it even, when you don't even have a classical spacetime here and you do not have a notion of time, what does it mean to ask questions like, what is before this? Like here it makes sense, what is before this? You know what it is. It is psi of chi comma A at this point, fine. Which satisfies the here in this case, emergent Schrodinger equation. Over here, what does it mean to say what is before and after when you don't have a notion of time? And if that, then what does it mean to talk about singularity, this kind of stuff? And one point, yeah, that is one thing. And one more thing over here is, you see, this is a mini Wheeler-DeWitt state supported in a boundary which is very small. And according to this this finite bit of holography thing, this is supposed to have information about all of this. Now I could have thrown an elephant or a pig or anything as long as the mass is the same. And this seems to imply that they should know what went into the black hole. And how can a very small object know what went into the black hole? The answer to that question is the same to answer another question, to the answer of another question, which is, if you live in a closed state, the entire wave function of the universe is described by one Wheeler-DeWitt state. So how do we see many different states? And the answer for that is the following. Is that the state is actually superposition of many different WKB states, and if each of this WKB state will have equal of I, S, and psi n. So this is the classical part. So this is what Wheeler-DeWitt called as the different branches. And so now if the classical part, so this is a wave function of the entire universe, even the observers, experimental errors, everything is a part of the universe. So this would describe all the observers, all the detectors, and this would describe the rest of the quantum mechanics thing. So when subsystems of the universe, steady subsystems of the other of the same universe, they necessarily need not to see, they necessarily need not see the same state. What state they see depend on which branch of the Wheeler-DeWitt state you are talking about. So you have to really think about that you are living in one particular branch of the Wheeler-DeWitt state, and how do you know which branch of the Wheeler-DeWitt state you are looking at? You have to make measurements. And similarly, the Wheeler-DeWitt state over here is kind of like the Wheeler-DeWitt state of a closed universe. It has many branches, and they will have different branches will have different things falling in. And for observers over here, it looks like it is a Wheeler-DeWitt state with many branches. And for observers over here, they live in some specific branches. With respect to them, when they see stars falling in, that is it is indeed a neutron star that fell in. They see it is indeed a magnet or star that fell in. And that's the end of the talk.
I know Ted at least has a question. So.
Not a question, comment.
Please.
Okay, go on.
But I'm not sure, it's really about a different approach that addresses some of the open questions that were raised by your talk, but maybe it'd be better if somebody wants to talk about what you actually spoke about first, directly, I mean, questions about what you
I have a question about the end. This thing with the multiple branches.
Yeah.
Presumably in the region when the area of the holographic screen, as you call it, is very small, you don't have this WKB approximation being valid inside.
Yeah, if it is not, yeah, okay, go on.
So then this interpretation of having multiple branches with respect to
Yeah, so but you have to put the holographic screen only at the point where the gravity is classical from here to here.
Yeah, but you were trying to describe the states of the inside.
Yeah, so that meaning the induced Wheeler-DeWitt state on the holographic screen describes all the interior stuff.
But inside, if you go close enough to the singularity,
yes,
there are no WKB branches, correct?
Yeah, there are no WKB. So then maybe this will not be a WKB state, and so you have to push the holographic screen a little bit to the right. And or maybe it breaks down WKB approximation everywhere, but I'm saying in modality, you have to check for WKB approximation, and I think probably it holds because it holds far away from the black hole, right? So it holds up to some point, and up to what point it holds is where you put the holographic screen.
Okay.
So when you say it breaks down inside that area, you're assuming that somehow, for example, you don't have the Wigner distribution or something like that, because your states are still assuming three metrics. They're still being described in three metrics. So the three metrics are always there.
They're always there, but they're not WKB. They're not giving an emergent space.
So it's the dynamical notion that doesn't emerge classically.
Yes.
So space-time, but space is always there.
Space is always there in the abstract sense, but it's not giving a space-time. And this condition, since it goes of order of, if it goes as order of 1 by g Newton, what happens in the Wigner thing is that for a given position, the momentum goes away. Then you don't have semiclassical approximation.
But what justifies saying you're in one branch in this area?
Yes. So let me answer that with a thought experiment, which is like, for example, consider two observers, observer O and an external observer. Now there is an electron over here, which is in the state alpha 0 plus beta 1. Fine. The state, so we have to start talking about everything in this template. State of what system with respect to which observer. Always talking that template. So the state of this qubit with respect to this observer or with respect to this observer is this. Fine. And when any of them measure, they will get either 0 or 1 with probability given by alpha beta. Fine. Now you put both of these observers in one particular box, and then ideally the external observer can write down a quantum mechanical state. This is all like ideally what you can do, not practically, but still. So the quantum mechanical state of this whole thing would be O tensor product with alpha 0 plus beta 1, right? So now, and then you do an now the state of this guy is such that he always has promised to himself that he's going to make a measurement in 1 second. Fine. So when he makes a measurement in 1 second, the state of this with respect to this is either 0 or 1, but the state of this whole box with respect to the external observer is the following. Because this guy can evolve this unitarily with the entire unitary dynamics, and that would go as 0, 0, 0 plus 0, 1, 1. Where this is the state of the observer who thinks he has made a measurement 0. This is the state of the observer who thinks he has made a measurement 1. But the state is actually this whole thing with respect to the state observer E. Now, if I ask the question, hey, has the collapse happened or not? That depends on with respect to which observer. And with respect to the observer O, yes, it has happened. With respect to the observer E, no, it has not. No measurement has been made. The measurement has been perceived as interaction by the external observer. And now you ask this question: how would the observer O know which branch he is in? This, like, if now comes to semantics. This observer in this branch thinks he is in this branch. The observer in this branch thinks he is in this branch. So we are observers in some branch, and we think we are in that particular branch. Depending on that, we have to condition the WheelerDeWitt wave function and proceed. Yeah.
Bernard?
Oh yeah, if I could, I'd like to make a comment and also ask an elementary question. Okay.
Any question is fine. For now, no restriction to questions.
So the comment was just.
Bernard, may I say one thing before you go? Since we're now over time, so people, if you need to go somewhere, it will not be rude. You can get up and go. People want to stay and talk. We'll stay and talk.
Well, the comment was just that it's long seemed to me that there's no reason to believe, when you have a collapsing star or something that forms a black hole and Hawking radiates, there's no reason to believe that this semi-classical gravity should be a good approximation, except in the very early stages of that process.
Yeah.
People normally say you trust semi-classical gravity until close, until the black hole has almost evaporated. And I've never understood
exactly
what their justification is for that. So I just want to say I'm very excited about what you told us, because it gives us, or seems to give us, a framework in which you can study that question.
Very beautiful.
So that's I didn't just long think that I put it in a footnote in a recent paper. So my other question, could I write on the blackboard? It's just a very elementary question.
Now, I'm going to be here until the last person leaves. So any question?
So just about your motivational
I'm going to bring that board
story where you
want the board?
oh, okay. Okay, so if I can clear a little space here or something. So you said to study a simple model with 2 degrees of freedom, right? With little q and big Q, and little p and big P, and I guess you have a Hamiltonian, like, supposing these are just 1 degree of freedom, so particles moving along the line, okay? So you'll have a Hamiltonian like p squared, little p squared over 2 little m, plus big P squared over 2 big M, plus V, which let's say is a function of little q minus big Q. Okay? Translationally invariant interaction. Okay. So, what did I want to say? Yes. So it seems to me that the analog in this system of semi-classical gravity would be, you'd have two equations, right?
Yeah.
One is the analog of quantum theory in a fixed curved spacetime, and that would be I h bar d little psi by dt is little p squared over 2 little m plus v times little psi, right? And the other one, which would be the analog of semi-classical semi-classical Einstein equation, would be big M q double dot, so mass times acceleration, Newton's law, right? But that's for a classical q, is then the expectation value minus dv by d big Q, okay, in some state. So, just for pedagogical purposes, it wasn't clear to me that you completely showed these two things. You did an approximation where these two things both emerge, or maybe I missed something.
So this thing is
this thing you showed
this, yes, and on this thing,
but this thing you didn't.
This thing I just showed this is equal to 0 at that point of the top. But I can show this one also.
Oh, maybe I missed it. What you showed this
equal to 0 without the back reaction. I showed that equation, and that in the Hamilton-Jacobi formalism is nothing but this equation.
It's still there. It's OGN minus 1. Here, OGN minus 1. You see the Hamilton-Jacobi equation for S naught.
You're saying that's equivalent to this?
Yeah. It's the same classical mechanics.
Where's the expectation?
Oh, no.
That is in the board that I erased over here.
But if you want to
back reacted
Hamilton-Jacobi.
Could you drag that one back into the next order in this normal?
No, it's not coming out. It's not like I don't know what I'm doing wrong with that. But I need to think. Like over here, if you go to the next order, I don't know whether we have to think about it as we still have a classical spacetime, and in which we are getting corrections to the QFT curved spacetime, or should we think about the notion of classical spacetime is starting to break down? These two things. We have to make a discussion in a big group to talk about that.
Do you know what Cauchy does? I forgot. Like he has the next order of this. I don't know. I think it's my memory. I didn't check, but my memory is that it is the expectation value, not the breakdown of. And then the other order is a breakdown of spacetime.
So I just want to say, if you could sort of show how you do an approximation on this that gives to these two equations, I think that would be very helpful pedagogically.
Okay. Yes,
You
it is.
understand?
That's good. Like I could have.
And then what you do for gravity is just like an analog to that.
I could have changed this, gone from this Hamilton-Jacobi formulation of classical mechanics to derive this thing. Yes, but I was just sacrificed it.
Where is the I'm still a bit confused.
So
Where's the
once we have
expectation?
classical, okay. So now once you have a function, and this is maybe not the right way to say describe what Hamilton-Jacobi equation is, but this is how I understand it. You have some function, f, any function, and you have a rule. The rule is for a given q, you know where the particle would be in the next instant of time.
Yes.
Because you get it's mx dot from the derivative of that function with respect to x. So you know where it is in the next point. And now that function, you know it everywhere. And now you take again, rely on that function and find its derivative with respect to this q. So you know what is q dot, and so you know where it is. And similarly, you can construct a path. Fine. Now the statement that this path is satisfies this equations that we wrote down is equivalent to the statement that this function f satisfies the Hamilton-Jacobi equation. I'm just stating it as a thing, but I can do a calculation on a paper and show you properly.
I mean, I think in this example you've chosen V as if it's a background potential and not an interaction potential. If you put an interaction potential, then surely it would have to turn up as
I
an
don't see where your expectation
expectation.
value is.
In the classical, in the toy model, I did not take the back reaction into account. So you're not
I
seeing.
think that would be a nice thing to do. Just
to say
to explain what the ideas are in this simple model. To exploit this simple model as much as you can.
Okay.
then when you come to do the quantum gravity, you can point to the
So
way
the
the
simple
analogy
model
works.
also you can consider Wigner's
You
function.
see what I'm saying?
Yeah, you can consider Wigner's function of small q, capital Q, small p, capital P, and take the reduced Wigner function of capital Q and capital P, and over that, the requirement that it has to be a Dirac delta would the same analysis visually.
But what's the motivating?
Maybe. Wait a second. As chair, Ted has been waiting very patiently to make a comment. I'm going to let Ted do that, and then we will officially close, and everyone can mop the board and talk to Rifath
Well,
informally.
actually, maybe it's worth just saying publicly the comment or slash question. So, the way I learned how to get the semi-classical Einstein equation was from like path integral or propagator or something, and like I read about it in Burrell and Davies' book.
I read the book, yeah.
And so, you get an effective action, you differentiate with respect to the metric, the renormalization of the stress tensor is taken care of kind of consistently within that formalism as well. And that's like kind of orthogonal to what you're doing because it's a covariant approach. But I wonder whether you can actually make it non-orthogonal by just saying, well, look, if you hand me a solution to the Wheeler-DeWitt equation, I know one way to get those objects is to do a path integral over the action. Maybe all solutions are given to the Wheeler-DeWitt equation can be written as a path integral with the covariant action with some initial state sewed on to the beginning of the path integral. That's probably true, at least formally. So if that's true, then it seems like another technical approach to the whole set of questions would be to just manipulate that path integral in the way Burrell and Davies tells us how to do it. And then we would solve the issue of, independence of lapse and shift, covariance, renormalization of the stress tensor, and how to get the semi-classical Einstein equation. Is there a reason why that's not answering the question that you set out to answer by your methods?
I just didn't think about that yet. We can think about everything in path integral formulation. Yes.
But I thought that your big contribution, which I didn't, at least I wasn't aware of before, is the sub-region classicalization, right? That I have not seen explained before. I don't think that's in here on data. So.
No.
Okay, let's thank Rifath again. It was incredibly quick.
One last point is, why should we trust the result that comes from Wheeler-DeWitt equation? Of course, it's a canonical transformability. Why should we trust canonical transformability? And our point of view is that in quantum holography, we wrote down the Wheeler-DeWitt equation as a partition function of a field theory, and it was in terms of a deformation from a CFT, and the deformation was an irrelevant deformation, and it satisfies the Zimmermann-Zig equation, and so it is RG flow, and so it is an effective field theory from the perspective of the field theory side, and so you have to actually, what it really is saying is that Wheeler-DeWitt states are just states in an effective theory of quantum gravity, and whatever model you have, whether it is loop quantum gravity or a string field theory or asymptotic quantum dimension or blah blah blah, whatever it is, effectively has to be like canonical quantum gravity is what we think right now, kind of thing. So it is useful to do these kind of things and learn about the real world. Point over. Thank you.